Hi there guys, welcome to this video where we're going to take a look at some A-level mathematics, and in particular we're going to be taking a look at hypothesis testing in this video, and a very specific part of hypothesis testing. We're going to be taking a look at finding critical values and critical regions of hypothesis tests on random variables that are binomially distributed. Okay, so it's a very specific aspect of hypothesis testing, and the reason that I've decided to make a video on that particular aspect of hypothesis testing is that so many A-level students, in my experience working one-to-one with A-level math students, so many A-level students come to me having difficulty finding critical values, critical regions for hypothesis tests for binomial distributions. And for me, in my opinion, the reason for this is that there is a fundamental lack of understanding in a precise enough sense about what is meant by a critical value. So I'm not by that suggesting that the people that come to me with this issue have no idea at all what a critical value is. It's just, it's not clear enough to them. Okay, it's not precise enough. Until they get a precise enough understanding of what is meant by a critical value, they've got no chance of finding one, basically. And this applies in a wider sense in mathematics. So this doesn't just apply to hypothesis testing, statistics, but in mathematics in general. Whether it's trigonometric functions that you're dealing with, whether it's moments of a force about a point, or whether it's critical values in hypothesis testing, if you don't know what these things are in a precise enough sense and what some of their properties are, then you've got no chance of using them effectively to solve problems. And you can't solve problems involving these things if you don't have a precise enough notion of what they mean. So if you don't know what is meant in a precise enough sense about the moment of a force about a point, you're not going to be able to use it to solve problems, and you're not going to be able to solve problems involving it. Same for trigonometric functions, same for critical values. Okay, so that's going to be one of the first things that we're going to have to address. We're going to have to really figure out what do we mean in a precise sense about critical value. I'm not going to be going right back to basics with hypothesis testing in this video. It's not meant to be a comprehensive rundown of all aspects of hypothesis testing in A-level maths. I'm going to assume that you do have some basic understanding of what is meant by a hypothesis test. Maybe you've done a few hypothesis tests from the exercise in your textbook or whatever in your classroom, so that you've got a little bit of experience with hypothesis testing, but maybe you're still struggling when it comes to finding these critical values and critical regions. This video is not meant to be giving you a nice cheaty shortcut way of finding critical values or anything like that. It's not intended to be a video where I just give you a set of steps to follow that you don't have to understand, but if you follow them, you get the critical value and things like this. There is going to be some level of understanding required to follow what I'm saying in this video. You may need to take notes. You may need to think carefully about some of the things that I say and some of the things that I write on the board. If you're looking for a quick fix, if you're looking for a nice shortcut method, this is not the video for you. I don't do shortcut approaches. The way that I present mathematics, whether it's A-level, whether it's GCSE or otherwise, is through understanding. I encourage depth of understanding, so that you can solve problems effectively and confidently. I don't encourage people to rely on cheaty shortcut methods because they're a waste of time. I don't do them, okay? So this video is not meant to be anything like that. It's based on developing a sound understanding of the concept of critical value, okay? So, first of all, we're going to have to make sure that our hypothesis test is set up correctly. Okay, so there's some basic information that we need before we get started. We need a random variable. We need a distribution for that random variable. We can't do a hypothesis test on a random variable that doesn't have a distribution. Okay, that's not to say that we know what the distribution is, although in what we're going to be doing, we assume that the distribution is a binomial distribution, but we have to assume, to do a hypothesis test, you have to assume as an absolute minimum that there is a probability distribution, whether known or whether unknown, that is attached to that random variable, or to that thing that we're calling a random variable. So we've got a binomial distribution. That means that the two parameters n and p. We do our hypothesis test on the value of the parameter p at A level. So we've got a null hypothesis, which says that p is equal to some constant value p naught. And then we've got the alternative hypothesis, and there's three possible forms, two of which I'm going to be concentrating on in this video, one not so much. The two forms that I'm going to be looking at are the following. Alternative hypothesis that p is less than p naught, and the form of the alternative hypothesis that p is greater than p naught. Okay, I'm going to be looking at those two cases. They are separate cases, and just for reference, the third one is that p is unequal to p naught, which, as you're probably aware of, is just kind of a combination of these two. Okay, we also need a significance level. So I'm going to denote my significance level as alpha. Now, whereas very often the significance level is expressed as a percentage, I'm going to insist that the significance level in this video is going to be expressed as a decimal, just for the simple reason that it makes for less clutter when it comes to some of the calculations that I'm going to be doing. Makes them a little bit less fussy, a little bit less fiddly. So this is a decimal. So instead of 5% significance level, we're going to express the significance level as 0.05 instead. So let's get rid of that, because we're not going to be really dealing with this too much in this video. And without further ado, let's get stuck in. So I've been going on about how important it is to understand in a precise sense what it means for something to be a critical value, a hypothesis test. Well, let's have a look now at what we mean for something to be a critical value for a hypothesis test, and how we can precisely identify what the critical value is going to be. Okay, so be prepared to take notes in this part of the video if you need to. Be prepared to watch bits of it again, whatever you need to do. But there's going to be quite a lot of information coming through potentially. If it's kind of new to you, there's going to be quite a lot of new stuff coming through. So I'm going to give, let's take a particular random variable y, which has a binomial distribution with parameters 20, and the null hypothesis is that p equals a half. P equals 0.4. Let's go for 0.4. So that's the null hypothesis. The alternative hypothesis, we're going to be dealing with this case initially. So let's assume, therefore, that p is less than 0.4. And let's set a significance level of alpha, which equals 0.05. Very typical. Okay? We want to find the critical value of this hypothesis test. Well, I'm going to illustrate first with a kind of a much more subjective example of what is meant by a critical value, and then we'll take a look at this. So let's say that I'm playing a game where I flip a coin, and initially I assume that the coin is a fair coin, but as I'm flipping the coin, what I realize is that I seem to be getting fewer heads than I would expect to be getting. And this is just personal, subjective feeling. But it's something that I've noted. So what I suspect is that the probability of getting head is less than a half for this particular case. Okay, so we've got w, which is my random variable, and I set up an experiment, a very simple experiment. I'm going to flip the coin 50 times. Okay, so w is my random variable, which counts the number of heads that I obtain in 50 flips of a coin. I assume that the coin is a fair coin. So this is my null hypothesis, effectively. My alternative hypothesis is that the probability of obtaining a head is less than a half. Okay, so half here is the probability of obtaining a head. And I'm not going to set a specific significance level because this is my subjective feeling, but there is effectively a significance level determined by me in a certain sense. So I plan to flip this coin 50 times, record the number of heads. Before I do that, what I say is that if I obtain 15 heads or fewer, then I will believe that the coin is biased. If I obtain 16 heads, that's fine. Okay? This establishes, therefore, a cutoff point between me accepting that the coin is, or believing the coin to be fair, and believing the coin to be biased. Okay? So, effectively, 15 is in my rejection region, because if I get 15 heads, or 14, or fewer, or whatever, then I reject the null hypothesis, which is that the coin is fair. Okay, that's the null hypothesis. I'm assuming that the coin is fair. So effectively, I have set up a significance level here. So what I'm saying is that if the probability of me obtaining 15 or fewer heads, and notice it's not the probability of obtaining 15 heads, it's 15 or fewer. So it's that outcome or something more extreme than it. If this probability is too small, then the coin is biased. Okay, so reject H0. If, on the other hand, I go to 16, I'll find that the probability is just right, or it's large enough, and therefore the coin is fair. When I say that the coin is biased and the coin is fair, these are not absolute assertions that I'm making. These are just my belief based on the evidence that I receive. A hypothesis test, the conclusion that you derive from a hypothesis test can never be definitive. Or it shouldn't be, because there's always the possibility for error. Okay? You can flip a fair coin 50 times and obtain 10 heads in 50 flips. There's a non-zero probability that this is going to happen. You could flip a fair coin 50 times and obtain 0 heads, in theory. There's a non-zero probability of that happening. It's very unlikely. Okay? If you do in practice flip a coin 50 times and get no heads, this happens so infrequently that you would be led to believe that the coin is actually biased. Okay? That it's a dodgy coin. But it might still be but it's still a fair coin. Okay? Potentially. So the outcome of a hypothesis test doesn't ever say what is or is not the situation. It just says what the situation may or may not be, with the accepting that there is the possibility of error. Type 1 errors, type 2 errors, which I'm not going to get into in this video, but they're a thing. If you want to read more about those, do so. Okay, so this would be my critical value for this particular personal hypothesis test that I'm doing. This kind of wishy-washy hypothesis test, subjective hypothesis test. This would be my critical value. W equals 15 is the critical value. W is less than or equal to 15 is the critical region. Okay? So how do we do it when we've got a specific significance level, a number attached to our significance level? How do we deal with that now? How do we bring that into play? Because this will tighten the whole thing up and make it a bit more objective, because here I might decide that if I get 15 or fewer heads, then I'm going to accept that the coin is biased. You might accept 15. You might go as low as 10 before you start to say that the coin is biased. So if we get 15 heads in 50 throws, I'm saying, no, I think the coin is biased, and you're saying, no, I think it's still a possibility that it's fair. So this is too subjective. We need to tighten things up a little bit. So what are we looking for? Well, with our distribution here, y, what are the possible outcomes? If we do this experiment, what are the possible outcomes? 0, 1, 2, 3, 4, up to 20, right? So integer values from 0 to 20 inclusive. But there's going to be a value, an outcome that I obtain, k, such that the probability that y is less than or equal to k. So the probability of getting that outcome or something more extreme than it, where the probability of this is too small for me to accept the null hypothesis. What's too small? Less than or equal to alpha, which is 0.05. But if I go to the next outcome along, k plus 1, if this is greater than 0.05, that's my critical value. Okay, k is my critical value. And therefore, y is less than or equal to k is the critical region. So this is what I'm looking for. Where does this transition occur? And these are just cumulative probabilities. Okay, so bearing that in mind, how can I find these? Statistical tables or your calculator, whichever you prefer, right? And this is going to be dead straightforward because all I've got to do is just go to the binomial, the relevant binomial table, and literally scan across or down the numbers and see where this transition occurs. So let's calculate. Probability that y is less than or equal to 2, probability that y is less than or equal to 3, probability that y is less than or equal to 4, probability that y is less than or equal to 5. So I wouldn't have to write all of this stuff out necessarily. But now I just observe. So the probability of this is 0.0036. This is 0.0160. This is 0.0510. I may as well stop there because I've got the transition. This is less than or equal to 0.05 and this is greater than 0.05. So what's my critical value? It's 3. 3 is my critical value. What's my critical region? Y is less than or equal to 3. Okay? It's understanding that this is what you're looking for. This is what we mean by a critical value in a precise sense, at least in this case. Okay? So more generally, what we're looking for, if we go back to x, we're looking for where the probability that x is less than or equal to k is less than or equal to alpha, the significance level, but the probability that x is less than or equal to k plus 1 is greater than alpha. That's what we're looking for. In that case, critical value is k. Critical region is x less than or equal to k. And if you know this, you understand this, it's easy, straightforward. Let's have a look at the second case. So in this second case is where people really start to run into difficulties and their lack of understanding, not simply of what a critical value is, but also how binomial distributions work and how probabilities work and things like that. It really starts to show with the kinds of things that they do. So I'll give you a bit of an idea about what kinds of mistakes people typically make. So you might be able to catch yourself making these mistakes from time to time. You might start to understand a bit better why you're struggling to find critical regions or critical values. Okay, so we're looking now in this case. So again, suppose we've got y is distributed binomially, parameters 20 and 0.4. That's my null hypothesis. H1 in this case is that p is greater than 0.4. And again, I'm going to stick with 0.05 as the significance level. So this works in more or less the same way with the coin flipping. So let's say now I believe that the coin is biased in favor of heads because I seem to be observing more heads than I would expect. So I'm going to flip the coin 50 times. And let's say if I flip the coin 50 times and I observe 37 or more heads, then I will believe that the coin is biased. If I observe 36 heads, then I will still believe, even up to that point, I will still believe that the coin is a fair coin. Okay, again, it establishes a critical value, my personal critical value potentially for that particular informal subjective hypothesis test, but now we're going to tighten things up. Okay, so what are we looking for here? Well, again, integer outcomes 0 to 20. What we're looking for in this case is the probability that y is greater than or equal to some particular value k is less than or equal to 0.05. But the probability that y is greater than or equal to k minus 1 is greater than 0.05. Okay, and it's important to realize that the rejection region now, in this case, maybe I should draw it on a diagram up here actually. So I'm just going to use, this is just for illustrative purposes. I know that a binomial distribution is a discrete distribution, but I'm just going to draw it like this. And in the first case, the rejection region, so the distribution would be split into two regions. As you probably know, acceptance region and rejection region or critical region, which is determined by the significance level. Okay, so in the first case, the rejection region is going to be down here, and the acceptance region is going to be on the right-hand side of the distribution. Okay, so in that case, k would be here, k plus 1 would be here. That would determine my critical value, and then x is less than, y is less than or equal to k, or x is less than or equal to k, would determine my critical region. But in this case, we're up at the other end of the distribution. Okay, so we've got distribution roughly looks like this. We've got the significance level splits things up into an acceptance region, which is now on the left-hand side, and it's the larger region of the two, usually it's going to be. And then we've got the rejection region here, or critical region. So in this case, k is going to be just inside here, and k minus 1 is going to be here. So notice that these are not cumulative probabilities. Make sure you know what is meant by a cumulative probability. But a cumulative probability is one of the form probability that x is less than or equal to some particular outcome. I'll just use k again, but is of this form. That's a cumulative probability. And they're the kinds of probabilities that you see in your statistical tables charts. This is not a cumulative probability, nor is this one. Okay, now here's where the confusion starts to come in. People recognize that the critical region is up here. Okay, so what they rationalize this as, potentially, is that they're looking for a transition from where they kind of think of these as cumulative probabilities, and that they want to use the tables, and they'll look for a transition from where the cumulative probabilities in here go from less than 0.95 to greater than 0.95. Okay, and they'll think that that determines the critical value, and it doesn't, unfortunately. So let's have a look. If we take this approach, which is wrong, by the way, what will we see in this case? Okay, so I'm just scanning along now, so I can see that the probability that y is less than or equal to 11 is equal to 0.9435. And the probability that y is less than or equal to 12 is equal to 0.9790. So we've got a transition there from less than 0.95 to greater than 0.95. So there's all sorts of things that are going on in people's minds here. There's all sorts of poorly understood ideas, things that they've seen their teacher do, things that they've seen in textbooks, and everything's kind of got jumbled up and confused, and they've come to this conclusion that they can just go through the tables, maybe basing their idea about what happened in this case. They're kind of trying to just repeat that, just copy it in this case. And they're looking for a transition, but because the rejection region they realize is up at this end of the distribution, then it can't be a transition from less than 0.05 to greater than 0.05. it's got to be from less than 0.95 to greater than 0.95. And that's what they get here. And then, okay, they kind of say, well, this must be the critical value then. Y equals 11 is the critical value. And therefore, y is less than or equal to 11. Y is greater than or equal to 11 is the critical region. And this is wrong, okay? This is completely wrong. So let's have a look at how to do this properly. If you want to, well, maybe your calculator can find non-cumulative probabilities, in which case use them and just look for this change. But if you're like me, or your calculator does cumulative probabilities and only cumulative probabilities, just like the statistical tables do, then you're going to have to do something else here. You're going to have to fiddle these a little bit before you can figure out the critical value. So let's have a look at what we need to do. I'll show you what I would do in this case. So what this boils down to is if we've got the probability that y is less than or equal to r for this binomial distribution, plus the probability that y is greater than or equal to r plus 1, this must be equal to 1. Okay? And therefore, the probability that y is greater than or equal to r plus 1 is equal to 1 minus the probability that y is less than or equal to r. Big deal, right? Well, actually, this is quite useful because it means that now I can replace this with the expression 1 minus the probability that y is less than or equal to, so let's get this right, so that would be k, so this is going to be k minus 1. And similarly, I can replace this with 1 minus the probability that y is less than or equal to k minus 2. Okay, so in other words, I'm looking for a transition, which I'm not done yet, by the way. I'm looking for a transition from where this probability is less than or equal to 0.95 and this probability is greater than 0.95. 0.05, sorry. Well, this is inconvenient for me to work with. So what I'm going to do is I'm going to rearrange this inequality to get the probability that y is less than or equal to k minus 1 is going to be, let's get this right then, so that was over 1 minus is greater than or equal to 1 minus 0.05, which is 0.95. And this will become the probability that y is less than or equal to k minus 2 is going to be, again, let's get it right, less than 0.95. So I'm looking for a transition. It is a transition from less than 0.95 to greater than 0.95. But notice that it's not k and k minus 1, it's k minus 1 and k minus 2. Okay. By the way, I hope you understand where this comes from, this here. The outcomes, for a binomial distribution, you can split the outcomes into, all of the possible outcomes into two mutually exclusive events. The event that you get an outcome that is less than or equal to r, and the event that you get an outcome that is greater than or equal to r plus 1. These are mutually exclusive events. So the total probability is equal to the sum of their individual probabilities, but their total probability is also equal to 1 because it accounts for all possible outcomes. Okay, so this is what I need to look for now with the sales, because notice that these are cumulative probabilities. That was the whole point of it. I'm expressing non-cumulative probabilities in terms of cumulative probabilities. I'm deriving some inequalities involving non-cumulative probabilities. I'm deriving some equivalent inequalities involving cumulative probabilities. So now I can use the tables. Okay. So what do I look for? I get the probability that y is less than or equal to 11 is equal to 0.9. I've already written these on the board, haven't I? I've rubbed them off now. And the probability that y is less than or equal to 12 is equal to 0.9790. So that's where the transition occurs. That is greater than or equal to 0.95. That is less than 0.95. Okay, so that means that this is k minus 1. K minus 1 equals 12. So k is equal to 13. Okay, k is equal to 13. So that means that this is my critical value. 13 is my critical value. Okay. If we go up here, that means that 13 is going to be there. 12 is going to be in here. So there is a bit of algebraic manipulation that you've got to do, potentially, to figure out what the critical value is going to be. But it is important that you understand how these calculations work. If you don't want to spend the time figuring out how these calculations work, then it's your fault if you struggle to find critical values, because you need to understand this sort of stuff. I'm not saying that this is the only way that you can go about finding critical values, but you at least need to understand what is meant by a critical value, and you also do need to have an idea about how to manipulate probabilities for different distributions, the few different distributions that you come across, in particular, in this case, a binomial distribution. Okay, so hopefully that makes a little bit of sense. If there is anything that's not clear, do feel free to ask in the comments section. So if you don't understand, you don't understand, but that, as long as you want to understand, that's the important thing, right? It's ignorance is not something to be ashamed of, okay? It's if you have no intention of actually learning what you need to learn, okay? That's where you're going to have a problem, okay? So ignorance is nothing to be ashamed of. In fact, it's a perfectly normal thing. I'm ignorant of all sorts of things. If I can help you to understand better, please just leave a comment in the comments section and I'll get back to you as soon as I can. If you've got any ideas about anything else that you'd like to see me cover in some of these videos, please let me know. If you do find these videos useful, please show your support by hitting the subscribe button and clicking the like button. I don't make any money from these videos. I make them because I feel like making them, and I want to help you to achieve your true potential, to go on to do whatever it is that you want to do at university, at college, at sixth form, to get your exam results. That's what I want to do. Nothing pleases me more than to see my students and the people I'm helping achieve what they want to achieve. So that brings us to the end of this video. Thank you very much for watching, and I'll see you in the next video.